Hi troops. Aki speaking.
And Karubi.
We're looking at how K3MT explains S parameters. These are measurements of how our F power, fed into a network, is distributed to its outputs, and how much is reflected back to its source. Let's start with a 1 to 4-way splitter, used to distribute a cable TV feed to 4 rooms of a house.
These have 5 type F coax fittings, called ports. They're 5-port networks, used on a TV coaxial cable system. With a 75 ohm load on each output, they present a 75 ohm load at the input port. To work properly, the loads are needed.
The thing is a typical black box. A hacksaw can help open it to see its innards, though this isn't necessary. All we need know is that it scatters the input power to 4 outputs, and, as a circuit, can be described by a set of 25 measurements, called scattering, or S, parameters.
When we put power into it, part goes into each output load. Let's see how much. Number the ports, 1 to 5, with a marker pen. Though a strong bias tends to number the input 1, it really doesn't matter.
Put 75 ohm loads on all the others. Then, connect port 1 to a signal generator at a constant frequency. S parameters change with frequency.
Put some voltage, perhaps 75 mV, into the splitter. Then measure the voltage across every load. Call the input voltage, V in 1, and the 4 outputs, V out 2, to V out 5. These are usually not in phase with the input, there's a time delay in going across the network. They have both magnitude and phase. They're complex numbers.
Calculate the ratio, V out 2, over V in 1. This is called S21. Calculate S31, S41, and S51 the same way. These ratios are 4 S parameters of the splitter. The first subscript always means the output port voltage, and the second, the input port voltage.
Suppose we made a mistake, and put the input on port 2, with a load on all the others. Then, when we measure the voltages, we can calculate the ratio of V out 1 over V in 2, or S12, and 3 others, S32, S42, and S52. Then moving the generator to any of the 5 ports, and making the same measurements, gives us 20 S parameters of this network.
The input impedance at any port is always 75 ohms. A 75 mV input will produce 1 mA, in phase with the voltage. But, with some impedance imbalance, the current can be different. A separate 3-port network, an impedance bridge, can measure the difference. And let us measure the mismatch, a voltage reflected out of port 1, V out 1. You may have done these measurements using a vector network analyzer. It requires calibration of the bridge, with 3 separate measurements: open circuit ED, short circuit ED, and with a properly calibrated load.
The ratio, V out 1 over V in 1, is S11, the port's reflection coefficient. In the same way, we can measure S22 through S55, the remaining S parameters of the splitter. So it has 25 S parameters in all. An N-port network has N squared S parameters. By the way, the reflection coefficient is the parameter plotted on a Smith chart.
Let's look at a few examples. Here's a good one, an antenna designed for 50 ohm coax. It has only one port. So all we can measure is S11, the ratio V out 1 over V in 1. A perfectly matched antenna will have no reflected voltage. This means the reflected power, 0 squared volts over 50 ohms, is 0. All the input power, Vin squared over 50, is sent to the antenna.
If S11 is plus 1.0, the output voltage equals the input voltage. All input power is reflected back as Vin squared over 50, and none actually enters the antenna. Your antenna fitting is probably an open circuit. And, if S11 is minus 1, the antenna connector is probably shorted.
By the way, the standing wave ratio, or SWR, involves the magnitude of S11. SWR is 1 plus magnitude of S11, over 1 minus magnitude of S11. There is a standing wave of both voltage and current, though many insist on calling this ratio VSWR. Please, it's simply SWR.
Here's another example, an attenuator. It's a two-port network. S11 is the power reflected back to the signal generator. And S21, the reduction of power coming out the other side, is the attenuation, usually expressed in decibels. A proper attenuator will have S11 equal to 0. But take care, the decibel expression fails to include the phase delay, which sometimes is critical.
When S21 is 1/2 with a phase angle of 45 degrees, the power attenuation is 6 dB. And there is a phase delay through the device, almost always forgotten. But, not so with phasing lines.
Let's look at a piece of coax, 1 meter long, with a velocity factor of 80%. At 300 MHz, lambda equals 1 meter. The electrical length is 1 1/4 wavelengths. Suppose its loss was measured as 6 dB. It's an attenuator, the two ends, ports 1 and 2. When driven at port 1, 1/4 of the power appears across the load at port 2, 3/4 heats the coax.
The ratio of output to input voltage is 0.5, the magnitude of S21. But it has a phase delay of 1 1/4 wavelengths, or 450 degrees, 1 cycle, plus 90 degrees. Thus, S21 equals 0.5 at minus 90 degrees. The phase delay is quite important when designing phased arrays or the like.
Driven by V equals 2 plus J0 volts, its output is 0, minus J1 volts. And, as it drives a resistive load, the input and output current are in the same ratio with the 90 degrees phase shift. By turning the coax around, we get the same measurements, so S11 is equals to S22, and S12 equals S21. This two-port network has 2 squared, or 4, S parameters.
So, to wrap things up, measure the S parameters by terminating every port but one in the proper load resistance. Drive the remaining port through an RF bridge. Measure the voltage out of each port, and that received back from the bridge. Divide each by the voltage driven from the bridge into the input port.
Don't forget the phase delays. These ratios are the network's S parameters. It's really quite that simple. By the way, you can reach us through Mike, at K3MT, at arrl.net. So this is Kurubi.
And this is Aki.
Saying, bye, for now.